And so what I'm really going to be doing here, one of the motivations is, I think one of the most exciting developments in modern astrophysics has been the recognition of the rich diversity of architecture of planetary systems. We really had no idea that we were going to uncover this 20 years ago when we found the first exoplanets. And because this pattern is extremely rich, we have to kind of map it out. And that means that we have to learn a great deal about how, the properties of the stars influence the properties of the planets. Another important thing that sometimes gets lost here is, in fact, detecting planets is actually remarkably hard. We do it, it's actually difficult, and the planets that we can see may not represent the underlying population. And so as a result, I'm kind of going to be going through by beginning reviewing how one might actually detect exoplanets, the most common techniques for doing this, and the biases in them. I'm then going to be stretching to what I'm calling, a colleague of mine at Ohio State, Scott Gowdy, calls the race to the bottom, which in this particular case is the emphasis on the lowest massed stars, which turn out to be templates for really trying to understand analogs of the solar system that we can measure. As it turns out, one of my hidden themes is going to be, in fact, that it's very difficult to find real solar system analogs and characterize them properly. With that, we can then move to the discussion of the properties of stars and how well we can measure them. And I'm going to be distinguishing between measurements that, in my view, are fundamental ones, that is to say things where we actually have a real fundamental benchmark that we can apply to them, and ones that are strictly model dependent. It's important to know the difference between those two in astrophysics. Okay? And so to kind of begin with, it's kind of useful to have some kind of characteristic scales for exoplanets. And so kind of give you a sense of what you might expect to be looking at. I'll be giving you a few representative numbers that will turn out to be useful. You can look at analogs like Jupiter. And Jupiter has a mass that's about 10 to the minus 3 times the mass of the Sun. And this works out to be approximately 300 times the mass of the Earth. And this is kind of a template for a gas giant planet. The characteristic radius of Jupiter is about 10 to the minus 1 our Sun, which is roughly speaking about 10 times the radius of the Earth. And the next kind of characteristic scale you might worry about would be the scale of a planet like a Neptune or an ice giant. And in this particular case, you might have a characteristic mass that we might say would be of order 20 times the mass of the Earth, and a characteristic intermediate radius of about 4 times the radius of the Earth. And then finally, if you kind of go down to the Earth, to kind of get some emphasis there, you might say the mass here is about 3 times 10 to the minus 6 times the mass of the Sun, and the radius is roughly speaking 10 to the minus 2 of the radius of the Sun. And this is all. And the other thing to note here is your characteristic periods here are about 11 years in the case of Jupiter. And of course the period is about 1 year in the case of the Earth. And these very, very long orbital periods for the giant planets imply that you need extremely long campaigns in order to be able to characterize their orbits if you actually want to trace them out. And that's going to be a recurring theme here. Your sort of natural scales that you might have, the characteristic orbit of the Earth is going to be of order 1 AU. Characteristic orbit of Jupiter is going to be of order 5 AUs and beyond in terms of gas giant planets. And these physical scales correspond to extremely small angular separations for the kind of characteristic stars that we're actually looking at. And so one of the technical challenges of this is that the direct detection of planets is remarkably, remarkably hard because you're looking for very faint things very close to very, very bright things. And so as a result, I actually won't be talking about direct detection of exoplanets for a significant fraction here. Now you do have some characteristic methods that you might have. And one of these methods is you can basically measure the gravitational influence of the planet on the star. And so if you're not actually looking for an image, you can actually look at the reflex motion here. And this can be in 2 different directions. And one of these directions I'm going to kind of go over here to put this through as areas of topics of work, is with the launch of the Gaia satellite mission in particular, we will eventually be able to measure motions on the sky for giant planets. In other words, even though the orbital scales I talked about are extremely small, the Gaia satellite mission makes extremely precise measurements. Unfortunately, we do not yet have this release of the data, but in the next few years, we can anticipate that actually an interesting subset of possible future things will be happening using motions on the sky. However, for the most part here, what we're really talking about here is we're talking about measuring Doppler shifts. And so I'll be calling this basically the radial velocity method. Okay, and this is one of our kind of two major working tools for being able to figure out how we can measure the properties of exoplanets. Now, for this gravitational influence thing, there's kind of a useful kind of cartoon you can have, as you can imagine that you're looking over here. You have some kind of characteristic orbit that's going around some kind of center of mass. And at any instantaneous point, you're going to have your star, say it's moving towards you, and then you're going to have your planet, which is moving away from you. And the relative distances are going to be the distance to the center of mass. In this particular case, you can think of the Earth as being a useful benchmark. It has a velocity of about 30 kilometers per second, roughly speaking, in its orbit, with a period of about 1 year. And this implies a reflex motion on the Sun, which is of order 10 centimeters per second, which is just found by the ratio of the masses. And this is telling you that if you wanted to be able to find a real Earth-like orbit, you have to be able to measure motions within a period of a year, a characteristic amplitude of about 10 centimeters per second. By comparison, if you wanted to do Jupiter, Jupiter has a motion of more like 15 kilometers per second, roughly speaking, a characteristic period of about 11 years. And this then works out to a reflex motion on the Sun, which is about 15 meters per second. Okay? And by comparison here, the characteristic state of the art, the kind of astrophysical limit, in our ability to measure this, is of order 1 meter per second, roughly speaking. And this boundary, from a technical point of view of 1 meter per second, is largely set by the behavior of the star. There's also some question of your ability to technically measure it from the point of view of measuring the radial velocity shifts. But it's mostly the characteristic noise in the star. I have to remind my companions in the exoplanetary field that stars are not, in fact, constant light bulbs. They vary and they do things. And so as a result, these variability is, to us, astrophysically quite interesting. So ideally, from some people's point of view, they'd just be sort of like completely standard candles, but they're not, and this kind of gives you a limit. Now, the important thing here is if you kind of think about this physically, you have a velocity, which is going to be of order root gm over r, or the distance, and this implies that if you wanted to find a real Earth analog, you're going to have to look closer to a star or a smaller mass than you're going to be able to get in the solar system, right? So that's the first thing, is if you wanted to find real, honest-to-goodness Earth-like planets, you actually would have to look close or around a little star in order to be able to find them. Now, the other notes about this are that from a technical point of view, this kind of radial velocity method is, I would argue, first of all, it's relatively speaking expensive, okay? Expensive in the sense that you have to have long campaigns, you have relatively limited multiplexing, that is to say, largely speaking, you're doing one star at a time. These things have to be relatively bright, because the ability to make extremely precise measurements requires you to do some fairly elaborate technical challenges. And so these are, with all of these things in mind, this is the kind of characteristic set of limitations we have. But nonetheless, we found an enormous number of planets around other stars using this particular technique. Now, the characteristics of these planets are very striking. We found, for example, the existence of families of things like hot Jupiters. And we've also found kind of what I would call warm, eccentric Jupiters using these kind of characteristic radial velocity techniques. And to some extent, this has also been extended in our low-mass stars into the Neptune domain. And one of the things that I find the most striking from this, one of the things most beautiful, is that the dynamics of few-body systems are incredibly rich. And I think that that's been one of the lessons that we've gotten from the study of exoplanets. That if you have 2 or 3 Jupiters playing together in a complicated dance, you get an extremely intricate and unusual set of patterns.
Mark, can you define what you mean by hot Jupiter?
Okay. By a hot Jupiter, I would mean a thing would be a characteristic period less than of order 10 days. And for warm Jupiters, I would have basically inside what we call the ice line, which I'm about to define here. But this would be characteristic periods less than or of order a year, roughly speaking, typically for what I would call warm Jupiter. And the idea from both of these things is from what we believe in the context of planet formation, we think that you make these things in a domain where you have a lot of ices, you make them very far away from stars. And if you have something in a characteristic orbital period of 10 days, it's almost impossible to visualize how you make it there, and therefore, as a result, it must have been moved there by some kind of a dynamical process, either very early in the formation process or very, very late. Now, the important thing here is that this is measuring mass. And so as a result, we're going to need to be able to think about how well we can do with measuring masses. We'll come back to that. Now, another thing that you can do here by comparison is you can also look at transits. And the transit method has also been quite beautiful and quite successful. And in fact, the vast majority of the planets we know come about through the transit method. The basic idea here is, again, if I have a star in a characteristic place, I have a planet that's passing in front of it, I'm going to occult a characteristic piece of the surface of the object, and the dimming that I'm going to be seeing is going to scale, roughly speaking, as the radius of the planet divided by the radius of the star squared. And the reason for that is just that they're both at almost exactly the same distance relative to the surface area that you cover is like this. This implies that if I wanted to measure a characteristic Jupiter, for example, I'd have to be able to make measurements out of order the 10 to the minus 2 level. Okay? And if I wanted to be able to make a measurement of Earth-like planets, this would be of order 10 to the minus 4. Now, this is actually the design spec. This was the design spec for the Kepler satellite mission, is the ability to be able to make measurements, or the claim that we could actually make measurements at the 10 to the minus 4 level to spot transits that occurred once a year, 1 part in 10,000 drop in brightness, and the duration of an Earth-like transit is of order 2 hours. And this actually set the sampling time for the Kepler mission, which is basically 30 minutes. People like me are very pleased by these numbers because I'm interested in the oscillations of red giants, and it turns out that if you were designing a stellar variability engine where you wanted to study red giants, you would have sampled it every 30 minutes. And so it's absolutely perfect that by accident we got the timescales right. Okay, and so this is going to, by construction, measure the radius. And in contrast to the RV method, I think that there's some other important limitations that you have to worry about in practice. One of these is what I would call basically false positives. And there's a very, very, very long story in this game of what these false positives are. The basic problem is you're looking for a periodic dip in brightness in stars, and there's lots of things that can cause that. For example, low-mass stars turn out to be roughly the same size as Jupiters, and they cause a very, very similar transit depth. And so if you see a transit depth of 1%, it could be a star or a planet. You can't actually tell. There's also other more insidious things, like you can have a double star system behind your system whose light is diluted, and so you do, in fact, get a periodic dip in brightness that's very, very small just because you're actually looking at something else that's varying. It's actually fairly complicated. And these false positives are, in fact, typically more numerous than the detections, and there's actually a very, very complicated set of exercises people go through to remove them. That's something to keep in mind. The bigger kind of limitation here is that it turns out that from the ground, Your precision, that is how well you can do this, is typically of order 3 times 10 to the minus 3, roughly 3 millimags. And I'd contend that that represents just about the absolute limit of our ability to do differential measurements of brightness in stars from the ground. And that means that from the ground you could measure a Jupiter. In fact, there is a good industry of looking for Jupiter-like planets from the ground. But there's no way that you can actually measure Earth-like objects. Now from space, I'm going to say it's of order 10 to the minus 4. But this is actually one kind of not so widely advertised thing, as it turns out that the noise from stars like the Sun is in fact higher than we had estimated. And measuring real Earth analogs for Kepler is actually really hard. There's very, very few objects. I don't know if you'd agree with that, Eric. I think there's very few true Earth analogs that we can actually confirm using Kepler, given the noise model that we have for Kepler.
From the ground.
From space, even.
Yeah.
Yeah. But, it was, yeah. And so even though the mission was designed to do this, it turns out that because other stars are more variable than the Sun is, it actually turns out that the noise floor was higher than we thought it was for these Earth-like planets.
But I have to object, I'm sorry, about the ground precision. We can do better than 3 times 10 to the... We have done much better than that.
No.
We can get down to below 10 to the minus 3.
Okay, you can reach million.
But we can't do Earth-like planets.
Yeah. No, that's encouraging because this is the kind of characteristic benchmark that we achieve, for example, in stellar rotation studies, is this kind of characteristic precision. And so it is an area to work in that does actually get to be interesting because ground-based studies have certain intrinsic advantages over space-based studies, the most serious of which is actually the dwell time, the amount of time you can actually spend looking at studies. Now, one of the characteristic limits here is that you have to worry about the fact that you have a relatively small chance of an alignment. And this can be as high as about 10 to the minus 1 for a very, very large, for basically a hot Jupiter. So if you have an extremely large planet very, very close to a star, you might have up to a 10% chance of having one of these eclipses happening. And this is more like 10 to the minus 3 for true Earth. Okay, and so if you have a 10 to the minus 3 probability, that means that you have to observe 1,000 true Earth analogs in order to see a single eclipsing system, and that actually is a limit. Again, for the Kepler satellite system, this is why it had the statistics it did. It worked out that they wanted about 150,000 objects to have about 150 transits of Earth-like planets if all systems had such an object. Now, this is measuring mostly radius, but there's a couple of other things to think about. I can observe, if I have RV plus transit, I can necessarily measure the mass as well. And in fact, this is a big advantage because unlike the case of the RVs, which depend on the inclination angle, I know that the inclination angle is 90 degrees because I have an eclipse, right? So I therefore, as a result, can measure masses as well as radii. And in addition, I can use transit timing variations, or TTVs, to take advantage of the fact of the mutual gravitational effects between planets. If I see multiple transits, I can actually work out the timing variations and the masses directly. This is really a beautiful, beautiful technique, and a lot of our most interesting information in multi-planet systems, I think, comes from transit timing variations. Okay. And so the net results of all of this are that we found these unusual systems, and we went to Kepler. We found a large number as well from Kepler and subsequent missions. We also found a large number of smaller planets and a continuous distribution of radii, which is interesting because, as I mentioned, in the solar system we have these 3 characteristic radius scales. And in fact, the fact that we see a distribution of objects between Earth radii and Neptune radii is actually quite striking and quite informative. Okay. Now, the other things that you would like to have here now is this kind of points to the fact that you need high precision. And as a very good example of where this precision could be useful, there's going to be the problem of what I'm going to be calling super Earths. Let's say I have a bunch of objects with radii of order, say 2 Earth radii or something like that. That's not a natural scale for either Neptune-like planets or for rocky planets. It's kind of intermediate in size. And you'd like to be able to know whether or not the object you're looking at is actually basically a eroded core of a Neptune or a supersized Earth, right? And then to be able to make that distinction, you need basically very, very precise radii in order to be able to solve. Now, given what I've just told you, although we can technically make these measurements for a huge number of planets, it's very hard to find real Earth analogs. And so one of the things that you might want to look at is you might want to look at some characteristic scalings. And so this is going to be looking at basically the argument of what we call a habitable zone. And so the idea here is you might want to look at Earths that have Earth-like climates, but that's very hard to do. And so you might instead look for cases where you have Earth-like fluxes. That is to say, where basically L over 4 pi d squared is equal to L sun divided by 4 pi d Earth squared. Okay? And this is going to give you a characteristic scaling, a habitable zone scaling, relative to the habitable zone of the Earth, which is going to scale as, roughly speaking, the square root of the luminosity of the star divided by the luminosity of the sun. And you can actually have a very, very similar scaling for the ice line, which is basically where you have ices for planet formation. And this is important because stars have an enormous dynamic range in luminosity. And so as a result, if I can choose stars that are intrinsically fainter, I win in every dimension of this problem. Okay? My radii of the stars become smaller, and so as a result, the depth of transits becomes larger. The characteristic time scale for the period gets shorter, and so as a result, I have more cycles available to me to do this with. The characteristic mass of the star gets smaller, the velocities get larger. Every dimension of the problem becomes easier if you're looking at lower mass stars. And this leads, therefore, to basically a race to the bottom. Where the game amounts to basically seeing what's the smallest possible star that you can look at, and that's the best possible place to find planets, right, is actually this kind of characteristic line here. There are, of course, other issues, however, as we'll get to this race to the bottom. You can count me as a mild skeptic in terms of the overall wisdom of this particular approach. One of them is quite simply that very, very small stars are intrinsically faint, and that actually means that we don't know very much about their properties. We know much less about their properties from a technical point of view. And so one of the characteristic problems that you might want to look at in a program like this is, therefore, how well can we understand very low mass stars? In other words, how well can we measure the radii? How well can we measure their temperatures? Can we measure their abundances? Can we measure their ages? How well can we characterize their properties in general? This turns out to be technically challenging, and it's actually one of the reasons why I think we're focusing on in this program is these kinds of stars. They're really interesting, but they're very, very poorly studied, very difficult to study. Now, the other things that you might want to measure from this is you might want to measure, say, the radius and the mass of your star. And this, of course, has a direct scaling with the radius of the planet and the mass of the planet. So it's fair to ask how well you can understand these, how well you can measure these in the case of stars. You might also want to measure the total energy output, or the luminosity. And for reasons I'll get to, also the activity. And these things might be related, for example, back and forth to this question of habitability. In other words, if I'd like to know where I would find Earth-like planets around a given star, I have to be able to know how bright it is, how much energy it's putting out in the spectrum of energy that's actually emitting. You might also really want to be able to measure abundances, because you can imagine that this process is sensitive to the abundance, and of course you might like to be able to measure ages. And so these are all the kind of characteristic global properties of stars that you might actually want to care about, that you might want to characterize for a program like this. Now, one of the things that's difficult, particularly in an interdisciplinary sense, is kind of the limit behind, is to kind of emphasize how well one can do things, both in the best case, but also in the practical case, in the general case. And so I'm going to try and kind of give you a sense of both of these in terms of how well I could actually go about making these measurements if I had all the information I wanted, and how much information I have in general available to me to study exoplanet hosts. And this has been a case, by the way, where our ability to do things has been just exponentiating recently. It's one of the reasons why this is such an active field.
Mark, could you say a little bit more about ice giants for those who might not know the distinction between Jupiter and ice giant in terms of mean density or composition?
Yeah. Okay. Yes.
Those who don't know their planets, other than the order in the solar system.
Yeah. Yes. Okay. So the basic idea here is if you look at the characteristic densities of planets like Jupiter and Saturn, they're of order unity in CGS units, astronomers' units, the real astrophysical units. 1 gram per cc, roughly speaking. And these kind of characteristic densities turn out to be those that you would associate with a body that's primarily made of gas. Okay, and it turns out that if you were to construct a manifold of planet solutions and you gave them a wide range of masses and a characteristic composition that's mostly made of gas, like Jupiter and Saturn are, they would be of order the radius of Jupiter and Saturn. They would be of order 10 solar radii for actually a wide range of densities. If you then, by comparison, were to plot up, so if I were to plot up a characteristic diagram here that would be, say, R versus M, okay, and this would be sort of 1, this would be sort of 4, this would be sort of 10. If I were to plot the ensemble of gas giant envelopes, I would have some characteristic thing that looked like this for an object that's mostly made of gas. That's why you call Jupiter and Saturn gas giants. If I had an object that had only a thin veneer of gas on top that was mostly made of ice, it turns out I would, by comparison, have a characteristic range of radii that was very, very close to 4, and rocky systems would kind of plateau out between 1 and 2, something like that, solar radii, roughly speaking. And so when you look at the objects of the characteristic scale of Neptune and Uranus, the interpretation is, in fact, although they look like gas giants from the outside, they're almost all ice and rock on the inside, with the characteristic composition that's very different than that of Jupiter. And the difference between these two also tells you something interesting about the time scale for the formation of gas giant planets, because these are objects that have thin gas envelopes and these are objects that have thick gaseous envelopes, and the relative numbers of these things tells you something about how quickly you assemble them, and it's therefore an interesting planet formation problem. Now, so I'm going to start, therefore, with this kind of piece, which is looking at stellar properties. I have these numbers already here. And then let's start to ask, well, how well can we do this for stars in general? Now, in this particular case, we have a fundamental relationship between the luminosity, the radius, and the flux per unit area, the effective temperature. Now, this is actually, I think, frequently a stumbling block for a lot of people when they're talking about stars, because if you look at a star like the Sun, it has, of course, no unique surface temperature. The light comes from a wide range of physical conditions, a wide range of depths. It's some sort of fairly complicated average. But if I can define an effective temperature, which is the flux per unit area, if I have detailed or good measurements of both of these quantities, the luminosities and the radius. And so from my point of view, I would count the effective temperature as basically something that is a fundamental parameter. In other words, I can define it precisely, I can measure it in stars whose luminosities and radii I actually know, and I can correlate it with observable properties. So that's actually a fundamentally measurable property. Some of the other things I'm going to get to, I'd argue, like abundances and ages, are actually not that way. They're derived properties, and you can't actually calibrate them in the same fashion. That's an important mechanical distinction. And so if I were to look at this, I think the temperature has several different beautiful, beautiful diagnostics. If I were to plot, for example, the flux as a function of wavelength, you might have a characteristic shape of a black body spectrum, make it a little bit steeper on this side, shallower on this side. And I could use ingredients like, for example, the color to basically infer the temperature. I can use the properties of black body radiation, Wien's law, things like that to be able to figure it out in a very, very elegant way. The other thing I can do is I can use the properties of spectroscopic lines. I know, for example, that the Boltzmann equation is going to tell me that the relative populations of different levels, of different excitation levels, is going to be a function of the temperature. And so as a result, if I can, yes, go ahead.
So Mark, I'm actually, I want to know a little bit more about what your definition of fundamental is, because effective temperature is such a complicated...
It's a flux per unit area.
Right, but you're going into measurements that are actually related to the local temperatures.
Oh yes.
In fact, the age and abundance would not be fundamental, and effective temperature is. Is that
it's calibratable in the following sense. If I have a set of objects, so for example, this is how this is done in the apogee survey. You have a set of objects where you have what you regard as a real set of temperatures. You have the full integrated flux measured, you have the radius known, and then you take your spectroscopic scale and you slap it on top, and maybe it's right, maybe it's wrong, but you can actually define a system to pull it into agreement statistically with a fundamental scale, so it's calibratable in that sense. Now, you're absolutely right that it's not fundamentally measured in the atmosphere. The kind of quantities I'm getting here are indirect, and that's actually kind of part of where I was going, is the atmospheric measurements are frustratingly indirect. But they're ones that can be put on the standard system. By comparison, I'd argue that we measure the iron content relative to the sun, but that isn't actually ever in a fundamental system. Because we have no objects where we can actually have an independent method apart from spectroscopy where we can make that inference.
So I guess it makes a philosophical difference in fundamental, is that there is some amount of iron in the sun, but an effective temperature is not something that...
Effective temperature is flux per unit area.
I was thinking sort of along this what Adam was thinking. Fundamental sort of bothers me, but it may be that we're thinking intrinsic. So it's not, effective temperature is not an intrinsic property of the sun. But I would use the word practical or...
Well,
just define it and say, I can give the definition.
This is why this is actually a really interesting problem for stars, because atmospheres of stars don't have a unique temperature anywhere. They're complicated averages, right?
So it's not an intrinsic property. But iron abundance is. There is, the sun does have some amount of iron.
Yes, but it's not a calibratable quantity.
We just might not be able to measure it.
There's no place we can check our math. And that's an interesting difference, and that's why actually the business of defining fundamental solar mixtures has been such a big issue in astronomy, because if all of our measurements are relative to the sun and people change their ideas about what the solar mixture is, all of the elements in the universe then respond in scale as far as we're concerned. The amount of oxygen doubles or it gets cut in half or whatever it is, depending upon these measurements. No, that's a great point. That's a great point. Thank you. And so in this case, I could say use the Boltzmann equation, and this is kind of one thing we would do, and say, well, I measure a bunch of different lines, and these things depend, the relative strengths depend on temperature in a predictable way, so this gives me some kind of a thermometer. And I can then use the Saha equation, where I'm looking at the combination of ionization and recombination. And then there's an even more convoluted chain of reasoning here, which is that this is related to density. Density is related to pressure. Pressure is related to gravity. And so as a result, if I do very, very careful measurements, I have some kind of a diagnostic in the spectrum of the surface gravity of the star that comes from the relative strengths of species of different ionization states. Right? And so this is the kind of characteristic kind of line of reasoning that we use in order to be able to do this. And in fact, this is, until very recently, this is actually one of the few direct measurements of masses that one can make in the spectra of stars, is through the surface gravities of spectroscopic lines. So in this case, I would argue you have a bunch of different diagnostics. I can measure radii and luminosities and a few fundamental calibrators, and I can get these. And then the other question is, how well can I actually do or measure a luminosity of a star? And luminosities are actually surprisingly non-trivial, because we have this detail. It's an atmosphere. And the Earth's atmosphere has the unfortunate feature of masking or blocking out certain pieces of the spectroscopy of this SED in ways that make it very, very hard to directly measure. And so as a result, if you can't actually make these measurements for this subset of objects here, then you're going to end up being a little bit stuck. And as a result, you're going to have to make some corrections for this. And so one of the things that you have to be able to do for luminosity is you're going to have to be able to basically correct for the spectroscopic energy distribution, the fraction of light that you can't actually see from the ground. You're going to also have to correct for dust and things like that. And this is actually one of these exasperating things from the point of view of stellar astrophysics, although fascinating to many of my interstellar colleagues, because galaxies have the annoying property that they're full of dust, and this dust blocks some of the starlight in a complicated selective fashion and messes up your interpretation of the data. And this is actually a real consideration. But the biggest issue by far, and this has been a significant barrier in terms of our understanding of things like the Kepler field, has been distance. That is to say, you only measure the apparent brightness of stars, and so as a result, if you're only measuring the apparent brightness of stars, you actually have surprisingly crude information about distances of stars, and so as a result, you actually have a hard time getting radii. And that's why, despite heroic efforts by people like Daniel, we've had historically large uncertainties in the physical radii that we associate with stars in the Kepler field, for example, on planet hosts. And these radius differences can be quite large. And so this is another place where the Gaia mission is enormous, because with the Gaia parallaxes, and in general also ability to measure motions, we've now switched to a domain in astrophysics where I would argue distance is the single property of stars we actually have measured the most of, instead of one of these things that we've measured the least of. There's an enormous suite of techniques that people have built up laboriously and painfully to indirectly infer distances due to a whole bunch of different techniques that are now no longer needed. They're roughly as germane as the ability to measure the astronomical unit precisely, which at one time was a frontier astronomical problem. And so I think another big topic we have here is really trying to ingest and make sense of the enormous amount of Gaia data and how much it's actually been able to improve our characteristic ability to make measurements. And so if you want a kind of a state of the art, in other words, you could say basically best measurements that you might be able to make here, which represents roughly, I would argue, the state of the art. Joel Zinn, who's been a student in residence here, and I, and Dan and Dennis Stella are about to be submitting a paper where we're basically estimating how well you can do this. And our best measurements are, roughly speaking, 0.5% in temperature, 1% in radius, and 2% in luminosity. And this represents, I would contend, the limit where we're actually running into our ability to make these measurements, to define them. I can make completely reasonable sets of choices that give me different answers at this kind of characteristic scale. And this represents our kind of wall, our veil of ignorance, as it will, for stellar measurements, is at this characteristic border. That's actually pretty good. However, there are some problems where you would like to be able to do better. We're working on that. Now, masses are historically much, much more difficult. Okay, and so a mass is a funny quantity because in some sense a mass is, of course, a fundamentally measurable thing if you have the right system. You can measure the orbits of stars and you can measure masses. The problem is that the number of stars where you can actually make these measurements are remarkably, remarkably limited. It's double star systems with orbital periods that are right. Okay? And so, typically speaking, if I was looking at kind of mass, or my ability to measure mass, that's the wrong color, special color, mass here. Typically, if I was trying to worry about the ability to measure mass, I could measure it, say, directly in things like binaries. I could also measure surface gravity from spectra, typically expressed as a logarithm of this, or log g. And there's a couple of new angles that have come in that actually are, again, objects that we can be talking about here. One of these is because I have extensive time domain data, I can actually characterize stellar oscillations. This goes under the rubric of asteroseismology. And in this particular case, the set of oscillation patterns that I see is going to be related very sensitively to the mass and radius through pulsation and stellar theory. Now, this is a beautiful technique. It's one that we've been able to apply directly in some planet search candidates. It's one that we can apply more broadly in the stellar context. And this represents, again, an exploding discipline in stellar astrophysics in terms of its broad applicability and use. And so another kind of reason why we want to be able to be having a get-together or talk here is to be able to tie together asteroseismology back and forth to the study of planets. Because after all, the same light curves that people use to find planets are the ones that you can in principle use to characterize masses and pulsational properties as well. So that's actually kind of a beautiful linkage and another reason why there's a great opportunity to have a meeting and to get together in a place like this. More often, however, what we do is we have an indirect estimate here. Linked to the theory of stars. And this indirect linkage is to take observed properties that are perhaps correlated with the properties that we care about and to try and relate them through things like isochrones or stellar models to be able to try and figure out what the characteristic masses that we look at are. And so this kind of leads naturally to the question of which aspects of this stellar theory are the most robust. And I was kind of trying to think of a general way of presenting this. And there's a very nice set of tools that you can use to illustrate this that I'll be kind of using to sketch out an argument as to which aspects of stellar theory give us very robust measurements and which ones are most challenging. Yes?
I think one more direct measurement that's probably worth mentioning here in this context is the average density of the stars known from the transit.
Yes.
That's a useful one.
Yeah, that's true. That's correct. This is, you can measure it through transits. It's conditional on the shape of the orbit, right? So you do actually have to know something about the eccentricity of the orbit in order to be able to interpret the density. That is true that you get that measurement.
It's also the fundamental measurement from asteroseismology, and comparing the two, you can learn something about the orbit.
Yeah, because in the case of asteroseismology, in asymptotic pulsation theory tells you that the spacing between modes scales as the square root of the mean density. And then there's also a second relationship, more imaginative than speculative, but actually extremely well workable, which is that the acoustic cutoff frequency of the modes scales as the surface gravity. And that combination actually gives you independent constraints on mass and radius from the two. And so if you want to be able to understand, say, which aspects of this problem are the most robust, in other words, where we spend our time, which pieces of this problem are the hardest, one of the characteristic things that you can do is you can look at timescales. And the argument is basically that the free fall timescale for a star like the Sun is a characteristic time of order 30 minutes or something like that. This represents the time it would take the Sun to collapse under its own gravity. And so as a result, to an excellent approximation, we can assume that there's hydrostatic balance or an exact balance between pressure difference and gravity. And this would take the form in spherical symmetry of dp by dr is equal to minus rho g, or basically minus rho gm over r squared. Okay, and that's going to be the characteristic a relationship that's applied almost exactly in stars. And one of the huge advantages you have in the study of stars over other systems, like, say, the Milky Way galaxy, is that stars are equilibrium systems. And so as a result, the assumptions of equilibrium are almost exact in the case of things like hydrostatic balance. In addition, I can assume mass conservation. That's to say dm by dr is equal to 4 pi rho r squared. And this first condition implies necessarily a high central pressure, given the characteristic gravities we have in stars. This gives you a measure of central concentration. And then I can have the ideal, I know that I'm going to be roughly speaking behaving like an ideal gas law. That is to say the pressure scales as the density times the temperature. And so what I'm going to be doing here is that these kind of basic assumptions are very, very close to being correct for sun-like stars in general. And then you might ask, well, what implications can you draw from these? Well, one of the tools that you can do is you can use the tools of what I'll call homology to make an extremely general argument, which is to say, let's imagine that I now transform to a set of dimensionless equations. And so, for example, this mass equation here is one, where I look at Q, which is basically the mass divided by the total mass, X, which is the radius divided by the total radius, little t, which is the temperature in units of the central temperature, little p, which is the pressure in units of the central pressure. I'll call it rho bar, which is the density, units of central density, and little l, which is L of r over L tot, right? So just make a transformation to a dimensionless set of equations. If I make this transformation to dimensionless equations, my mass conservation, for example, takes an extremely simple form. This would be dq by dx times m over r is equal to 4 pi rho prime x squared rho c r squared. And I can then rearrange this. I'll only do this for one of them in the interest of time. And this is then going to be equal to rho c r cubed over m, which is going to be a constant under the assumption of homology. Now this at some level gives you a dimensional argument, which is sensible, which says basically that the central density ought to scale as the mass over the radius cubed. That's dimensionally sensible. And you can do the same thing with the pressure equation in order to be able to show that the central pressure ought to be able to scale as m squared over r to the fourth. I then have the ideal gas law that relates these two terms, and this then therefore leaves me the ability that the central temperature ought to scale as the mean molecular weight times the mass divided by the radius, and the mean molecular weight is just basically for a fully ionized gas the average mass of a particle in AMU, right? So that would be 1/2 for hydrogen and 4/3 for helium. And so the idea of these scalings, or a good way I like to think about stellar theory, is that basically for a given mass, stars can dial up or down their central temperature, their central pressure, and their central density by an amount that depends on the radius. So as you dial your radius in and out, you regulate your temperature, you regulate your density, you regulate your pressure. Okay. Now, if you believe that stars are optically thin, or optically thick rather. Optically thin would be fascinating, sir. There's a reason why I don't work on exploding stars. If you believe that they're optically thick, then you can imagine that the amount of flux that I can carry, which is basically L over 4 pi r squared, ought to be some characteristic diffusion coefficient times some characteristic gradient in energy density. Okay? And this diffusion coefficient would have units of basically the characteristic velocity and length. And if you're dealing with photons, this energy density is AT to the fourth, where is the radiation pressure constant. And this yields the minus sign there. This yields the equation of radiative equilibrium then, which would be L over 4 pi r squared is minus 4ac over 3 kappa rho t cubed dt by dr. If I design a mean free path, L is 1 over kappa rho, and my velocity is just c over 3, roughly speaking, okay, characteristically. And so if I make this kind of characteristic scaling, and I fold these quantities in here, I have something that scales as t to the fourth over rho here. There's factors of r squared. And I end up with the luminosity, which basically scales as mu to the fourth m cubed over kappa. And this kappa can either be roughly a constant, or it can be very weakly dependent on radius, depending upon the form that it takes. The point here is that I predict the existence of an extremely strong mass-luminosity relationship based on stellar theory in a form that is virtually model independent. And so the existence of an extremely strong mass-luminosity relationship is a robust prediction of stellar theory. The problem here is that the radius that I derive here is not a robust predictor of stellar theory. It depends upon the interplay of all these various factors. And so as a result, one of the issues you have in the theoretical modeling is you would like to be able to go through, from the point of view of stellar theory, you would like to be able to go through to measure things like the radius and its sensitivity to your model physics. And there's many places where you can work on this. This could be related to the theory of turbulence. This can be related to opacities. It can be related to other things as well. I'm sure I'm doing on time.
A
few minutes, okay. Beautiful. Okay. Well, we're getting close, actually. Because the next thing to note here, just wanted to kind of finish this up, is in terms of ages. Ages, again, we know the age of the sun through radioactive decay. The ages of stars are extremely difficult to measure in general because they're uncalibratable. And so as a result, another significant issue we have here that we're going to look at is basically the age scale. So I'll put the ages over here. And the last note that I'll put over here to close would be kind of rotation and activity. And I put rotation and activity in here because one of the issues you have with ages is that all stellar age diagnostics you typically use are tied to nuclear lifetimes, and nuclear lifetimes become extremely long for low mass stars. And so as a result, if you're looking at the lowest mass stars, measuring their ages becomes almost impossible directly because they have almost no nuclear evolution. You need to find other clocks that operate on an interesting time scale. And in this particular case, the time scale that's interesting is the spin-down time scale of stars, or so-called gyrochronology, becomes short or comparable to the age of the galaxy. It's therefore an interesting diagnostic and another avenue we're exploring. And the last note here is I talked about habitability as if it was the bolometric luminosity of stars that mattered only. In fact, stars are active, they have flares, they have X-rays, they have activity of various kinds, and this activity could scale in an unpleasant way relative to stellar mass and age, depending upon how things work out, which could cause problems for the habitability of low-mass stars. And I'll stop there. Thank you.
Questions?
Can I point out another problem with low-mass stars is that they spent a long time on the Hayashi tracks,
Yes.
so we have these, shall I call them, Lugar Barnes planets, right, that have been roasted when the parent star was, 100 times its current luminosity, so habitable zone becomes this very tricky thing with low-mass stars.
Yes. One of the lifetime of gas disks is order 10 million years. That's the characteristic time scale for gas giant formation. Even terrestrial planet formation is about 10 to the 8th years, and these objects can have a time scale for formation or contraction that's longer than that, and therefore they can be born in an environment that's unpleasantly bright relative to their
In the Open Quantum Systems program, we spend a lot of time on non-trivial dynamics.
Yeah.
And we have a lot of tools for analyzing, strange signals that we don't yet fully understand. Do you have a database you can point us to with the time dependence of luminosity for stars, individual stars near each other that we can play with?
Yes.
How many terabytes would you like?
So I guess, I sort of, I quite naively had previously the idea that, we had some basic information about each star, but I didn't realize there was a dynamical signal for each star that we get access to. That's really quite exciting.
Yeah.
And so you mentioned some overall features in such a signal, but can you discuss like the level of randomness and chaos and those kinds of things that you measure and how you quantify that?
Yeah, because what you're looking at is there's a couple of different there's some significantly different important pieces. One of these would be the granulation or turbulence at the surface of the star, which imposes a sort of called a granulation signal, sometimes called a flicker. And this is dependent upon the surface gravity because the size of the cells scales as the pressure scale has. And so the point is that different stars have very different kind of granulation patterns, which are intrinsically stochastic. I also mentioned these oscillations. What I didn't mention is they're excited stochastically by turbulence. And so as a result, you basically have to, you develop a pattern over time. You fill in an envelope. And characterizing that oscillation pattern in detail is actually a really interesting problem for the precise measurement of the frequencies. And another is the stellar activity, which not only has cycles of the stellar activity, but also cycles in where the spots show up on the surface of the stars and how they manifest themselves. And so those are some of the big kind of time variable signals, and all of these missions are measuring this to kind of for an absurdly large number of stars for long, interesting time bases. So it's a great data.
Yes.
Yeah, that's great.
It's your tax dollars.
Mike Axel. On the gross properties of stars and their analysis here, the mass, the radii, and so forth, can you pick out a subclass that's more likely to have Jupiter planets?
What you can do is you predict a continuous scaling. In other words, you can predict a continuous spectrum in terms of stellar brightness. And one of the active research questions would be how the properties of things like the disks that form the planets actually scale relative to the properties of the luminosities of the stars. Observationally, it appears that the Jupiter-like planets are favored by more massive stars. In other words, the stars that are more massive appear to have larger ones, in some cases even super Jupiter. They appear to be more rare around the low-mass stars, but that may also, I have colleagues who caution me that may also just be simply a selection effect, that we simply haven't looked in the right place for the most distant Jupiters that are hard ones to find.
Thanks.
Those are strong trends of abundances, right?
Yes, abundances and mixtures and things like that.
Please.
Mark, my understanding of gyrochronology is it works up to about a gig a year. Do you see promise beyond it working?
The case, it's an interesting business because what happens with the gyrochronology is that the spin down of solar type stars is relatively fast. And so as a result, the solar type stars work up to about the age of the sun, and the detection of the spots themselves becomes an issue, possibly the spin down. If you go to lower mass stars, the timescales extend, and they can easily extend up to 9 or 10 gig years. And so, in other words, for sort of stars of half a solar mass or so, you could easily imagine that gyrochronology could be a working tool throughout the lifetime of the disk. The M dwarfs, the problem is that they don't converge, and so as a result, you confuse information from spin down with birth conditions, and so there's an intrinsic degeneracy between those two for the very low mass stars.
Thank you, Mark. Okay, see everybody.